Hello, everyone. It's me, Mr. Younger, again. This is me on April 8th, working on our noon Zoom meeting for my lab. I just wanted to go ahead and get started, and also, of course, offer the office hour that this is starting when we're done here. This week's lab is called the Ballistic Pendulum. It's pretty straightforward, where basically it's a method you can use, for instance, to determine the muzzle velocity of any kind of gun. In this case, we're just shooting a ball from a spring-loaded gun that's specifically made for this type of lab, and you push it in 2 clicks instead of the one, two, or three options that you have. You push it in 2 clicks, it fires outward, and then there's a pendulum hanging from it that's a rod of aluminum, and it's got a big plastic head and some counterweights on there that you can actually adjust so that you get the center of mass exactly right. We actually treated the center of mass as the point at which the hole in the device at the end of the pendulum, the top of the hole that the ball goes in, that's supposed to be the center of mass. I tested it with my finger, laid it on that spot, and it seemed pretty precise, so that's good. And that's actually how we get the what we call RCM, which is the radius of the center of mass of the ballistic pendulum. So I wanted to briefly explain how that lab goes, and I'm doing that via the Zoom meeting right now. So let me go ahead and share my screen with you guys. Uh, so here's the screen you're looking at, but the more specific one is this one. So this is the ballistic pendulum. Right here is the little cannon mechanism that we use in the class. This is the pendulum and the thing that catches the ball. So what happens is when you load the ball by putting it in right here in the spot, in fact, on the side of the cannon that we use, it's got a circle drawn just like this, so we'll know exactly where the center of the ball is, as well as the bottom of the ball is, as well as the top of the ball, all that good stuff. And over here, it has three little boxes. There's a box here, and a box here, and a box here. And those three little boxes show the different cocking positions you can put them in. The ball could sit right here, in which case it's not cocked at all. But if you push it back until it highlights the first box, then that's the weakest cock. If you push it back to the second box, that's the second weakest cocking position. And then if you push it to the third, that's the strongest and therefore the fastest cocking position for the cannon. What you're going to do with this lab is first you're going to take this ballistic pendulum, which can be angled upward so that it's horizontal, and it's got a little catch mechanism in here that holds it in place. You're going to put that completely out of the way so that you can tell what the muzzle velocity is to some extent just by firing it horizontally. This is just like the ballistic pendulum. Excuse me. This is just like projectile motion that we studied in a previous lab where you use the exact same cannon and you shot it out at various angles. However, in this case, we're taking one, you might not use the same ball, so we can't just assume that the muzzle velocity we found last time was right because we might be using a steel ball this time or use a plastic ball this time and a steel ball last time or stuff like that. So the main thing is we've got to do it again. We're going to set this to 0 degrees via this little hanging mass. Make sure that mass is not touching the tabletop. If it does, that actually causes a little bit of error. So you want to make sure the string is long enough that the hanging mass, which should be symmetric, by the way, where the hanging mass can hang down and be past this, and the string just crosses the compass reading, if you will, because it looks just like or not compass, but a protractor reading, because it looks just like a protractor there. And you want to set that at 0 degrees. When you do that, you're going to fire the ball outward. It's going to fall a distance delta y, which is measured from the bottom of the ball to the floor, and then we subtract the distance or the thickness of the actual piece of rug that we use for it to land on. What we're going to do then is we'll fire the projectile, see roughly where it lands, then where it landed, we put dead center of a rug directly on the spot where it landed, and then right behind the rug we'll put a cardboard box standing upward so it can act like a backstop. Now that we have that, we can actually just go ahead and fire it 5 times in a row and measure the distance from directly under where the ball leaves the cannon to where it lands. We can use that delta Y, which remember is the distance up to the bottom of that ball minus the thickness of the carpet. We can use that delta Y and to figure out how long the ball will be in the air, because since we're firing it horizontally, it has no vertical component of velocity initially. So it's just like dropping a ball from a height delta y. And using that kinematic equation that's relevant there, you can figure out exactly how much time it gets to fall from the height that it's at to the ground, because in that period of time, it's also going to be moving horizontally at the muzzle velocity, which, if I remember correctly, I think we're calling V0. Yes, you can see right here calling V0. It turns out the time is given by 2 times delta y over g. Again, delta y being the measure from the floor up to the bottom of the ball, and then subtracting from that the thickness of the rug. G is 9.8. Now, if you take the horizontal distance that it goes on average for 5 trials, then you're getting the best estimate of how far it could travel horizontally in that time. So velocity is distance divided by time. So all you got to do is divide that distance delta x, which is the average of your 5 trials, by the time, which is the square root of 2 delta y over g, and that should give you the muzzle velocity. That is the first value of the muzzle velocity for part A. Then for part B, we're going to actually allow the projectile, instead of landing out on a piece of carpet, we're going to catch it in this pendulum, and it's going to be caught in that pendulum. And it is a heavy pendulum that's not a typical pendulum, but the main thing is, all we have to know for a pendulum is we need to know its length, specifically its length to the center of mass of the pendulum, and that's why we've got RCM, which you'll see in the addendum that I give you. We've got all that data for you already. So once you've computed that part A muzzle velocity, you're going to then again determine the muzzle velocity using conservation of momentum with the collision. And you should be able to square those two. In other words, the initial velocity or the muzzle velocity from part A should be very, very close to the muzzle velocity for part B. If you get errors on the order of 10% or even higher, then you definitely did something careless. You made some mistake. The experiment just doesn't have that bad a error. So, again, this would give us the velocity to determine or excuse me, the equation to determine the velocity in part A. And then in part two or part B, whatever we're calling it, we're going to examine the ball, which has mass little m and velocity v0, which ideally we just figured out from part A, but right now we're pretending like we don't know it. What we know is conservation of momentum dictates that that momentum will be equal to the total momentum after the collision, because we're assuming the net external force acting on the system is zero, so therefore momentum should be conserved. Again, that's a factoid you're supposed to know. So the initial momentum is just the mass of the ball times the velocity, the muzzle velocity of the ball, and the final momentum, which is literally just a split second after the ball gets trapped in the pendulum. That's the big M, which is what they're using as a symbol for the mass of the pendulum plus the mass of the ball. It's not just the mass of the pendulum, it's the mass of the pendulum plus the ball, and it will leave with some new velocity V. Now that means this new velocity V, if you actually wanted to solve for it, assuming you know V0, it would be little m over big M times V0. That would be the new velocity. Now that new velocity is also responsible, along with the mass, for the kinetic energy of the pendulum. So conservation of energy tells us that we can set the initial potential energy at 0, and then therefore, the initial left-hand side of the conservation of mechanical energy is the potential energy is equal to 0, but the kinetic energy is not 0. It's 1/2 capital MV squared. And then it swings up, and in so doing, it sort of takes this little sweeper mechanism, which I'll show you right here on this diagram. It takes this little sweeper mechanism up to as high as it goes, and then that sweeper mechanism stays there. It's built to just sort of slide along. Now, the problem with it is it does include some friction. It's got to have friction, or else it's not going to stay in the position once the pendulum hits it. So once you fire that first shot, you've got an idea roughly what angle the pendulum is going to rise to. So if it came out to, for instance, 32 degrees, you'd say, okay, well, I know it's roughly 32 degrees. For safety, to make sure I don't miss any data, I want to lower it to beyond where I expect it to go so that it would actually be able to push up on it, and then I'd know that I got the highest angle. Whereas if I've got it up too high and it never touches it, I'd misread the angle that it's reading, which has no bearing on anything, as the max angle it reached, and that would be a problem. So what we do instead is we fire one shot, and that one shot gives us an estimate of what the angle would be, let's say 32 degrees, and then we don't necessarily record that one. We're going to move this angle slider thing down 2 degrees lower than what we got. So we had gotten 32, now we're going to move it to 30 degrees and fire it again. That way we can be somewhat confident that it'll move. But that being said, you should still pay attention to that particular slider and make sure that it has moved, because if it's set at the exact same spot that you set it yourself, then probably it never even touched the sweeper. So you actually need the little sweeping arm to indicate the highest angle it reaches. So once that's the case, then you'll know that it's reaching the point where all of its kinetic energy has been converted to potential energy, which is given by m times g times h, with m being the big M, and h being a number we can calculate based on the radius of the pendulum and the angle theta that the pendulum reaches. Specifically, h becomes r, center of mass, which is the distance from the center of the axle of the pendulum down to the top of the hole where the ball enters. That's the R, center of mass. And when that tilts up some angle, that becomes, instead of the vertical, it becomes the hypotenuse of a right triangle. And working out that right triangle, you'll find that the height would be R, center of mass, times parenthesis 1 minus cosine theta, which is where they got this formula right here. So this RCM times 1 minus cosine theta is really what capital H means. That being said, or excuse me, that's what H means, not capital H. That being said, now we can use this formula to determine what the final velocity, or excuse me, what the muzzle velocity is. So what you're going to do at that point is you're going to take 5 measurements of the angle theta to see exactly what the theta is on average over 5 trials. Each time you got to remember to set the little slider back to a smaller degree. And I'm telling you all this as if you're doing the lab, but you're doing it online, so you don't have to do any of this, but it's good because it gives you an idea of some of the intricacies of the experiment. So basically, you're going to do the first part, which is just a horizontal projectile motion. That's going to allow you to determine the actual muzzle velocity. You can see the carpet here. That's how the little box top or the cardboard box will be standing as a backstop. The projectile will fire out and land somewhere over here on carbon paper. The carbon paper will leave a mark, so we can measure the distance from directly below the cannon end to the distance where the center of the mark is. And then we do it again for 4 more trials, and we fill in the 5 trials here, and then we calculate the average of those 5 trials by taking this one plus this one plus this one plus this one plus this one, dividing by 5, putting the answer here. Obviously, you want to make sure it's in meters, not centimeters. The delta y, we're going to measure again. It's supposed to be measured up from the floor to the bottom of the drawing of the ball on the cannon, and then you subtract from that the thickness of the carpet. But in our addendum, we actually gave you the delta y, so you don't have to actually do any of that subtraction of the thickness of the carpet, because we've already done that for you. So in your addendum, which I'm going to show you in a second, you already have the delta y and don't have to worry about the intricacies of cutting out the thickness of the carpet. Either way, you're going to record that delta y here, and then you're going to use not this formula, but specifically this formula, equation 1, to calculate the muzzle velocity. So this is gotten from equation 1. Then you're going to do part 2, where you're actually engaging the ballistic pendulum, so that the ball will be fired into the pendulum. The pendulum is going to swing up and put that little sweeper up to the maximum angle that it reached, and then the pendulum will fall back down. So again, you'll need to catch that maximum angle each time. So the way we do that is we push it down about 2 degrees lower than the previous time. And again, that reduces the friction so that it's only acting for the last 2 degrees as opposed to the whole, 20, 30, 40 degrees, whatever you get. So it reduces friction and makes the experiment a little more accurate. And by actually noticing what the setting of the sweeper is add before you do the trial. If you find that the setting's still the same after you've done the trial, you can be pretty certain that it failed, meaning that the uh, projectile hit the pendulum, and then the pendulum swung up, but didn't swing up enough to move the little black arm. So we don't have any idea what the max angle it reached was. So that's the key intricacies of the experiment for part two. In the addendum, you'll see we give you the data for the mass of the projectile as well as the data for the mass of the whole thing, including the projectile, the ball, in other words, and we give you the R center of mass. So we do the experiment. We fill in for 5 trials to determine the max angle. You fill in theta 1, theta 2, theta 3, theta 4, theta 5. You take the average of those two by adding them and dividing by 5. Put that in. Degrees is just fine. Make sure your calculator, of course, is in degree mode. Uh, you take the mass of the little ball, which we recorded as 0.06578 kilograms. You're going to record that here, and you have the total mass, big M, which is the mass of the projectile, the little ball, plus the actual pendulum, the more physical pendulum, if you will. That mass is 0.31199 kilograms. We're going to put that here. And according to our addendum, the center of mass radius is 0.285 meters. So that'll go right here. Now you're going to record the muzzle velocity you got from part A from equation one right here, but you're going to use this equation 4, to figure out the muzzle velocity on part B, which is right here. So this is equation 4 you're using for this one. And then you got to do a percent difference to these two. The two should come well under 10% different. If they're 10% or even 9% or higher, you did something wrong from a calculational standpoint. So make sure you're watching out for that. Now, the best estimate in principle, if these two are in the ballpark of each other, which they should be, then the best estimate would be the average of the two, because there's two different ways. Neither one is necessarily worse than the other. I would sort of say maybe it's a little truer to do the part one. It's a little simpler part, so I would maybe weigh part A a little bit heavier than part B if I had to, but generally just take the average of the two. That's fine. If one got a really bad result and the other one got a really good result, meaning that you actually tested it versus theory and you think that result is more meaningful than the other one, then you might want to choose to put the best estimate to be that one. But in either way, if you don't just take the average, you need to explain to me exactly what you did for best average, best estimate, and tell me why. Uh, Otherwise, you need to tell me why you chose the average as a best estimate. But that's basically the lab. It then concludes with some questions that include derivations and stuff of that sort. Feel free to ask me questions to get help on that, but that is something that has to be done as well. Now that we've seen that, I'm going to stop this sharing and share the addendum that you get. So now I'm going to share the screen with my addendum with my addendum on it, and you see this is the lab 13, which ours is not 13, but the main thing is it was called 13 at one time. The lab is called Ballistic Pendulum Lab, and this is the addendum for it. Here's our delta X values that we use for the first table. Notice there's 5 of them. You have to take the average of that and enter that. Here's the delta Y that's already had the carpet thickness subtracted out of it. And then here's the data for the part two. And it turns out the angle, the max angle that it reaches in 5 separate trials is 36.5 degrees, 36.2 degrees, 36.2 degrees, 36.2 degrees, and then 36.5 degrees. That's your 5. So that's what you want to take an average of to get the best estimate of theta. This is your mass of the ball or the projectile, which is 0.06578, and this is should be in kilograms. I can't believe they put it in there with no units. I'm sorry. That should be kilograms. The mass of the pendulum plus the ball is 0.31199 kilograms. Again, that should have units on it. I apologize for it not. And the center of mass, length of the pendulum is 0.285 meters. This data, with this data, the muzzle velocity from the firing of the off the table was 4.88 meters per second. That's what we got when we did this. If you don't get the same result probably you're making a mistake. Same thing here. If you don't get the same result, you made a mistake somewhere. The muzzle velocity using the conservation of momentum turned out to be this. You can see they're very close. So, but that's basically it. It does have pictures of the landing spot. So there's where the little carbon paper dots look like when a ball hits. It leaves a ball shaped carbon paper mark. You'd measure to the center of that from horizontally from right where it leaves the cannon. And that's about it. That's all you really need to conduct this lab. You have the addendum that's listed in module 12, and you have the write-up, which is listed in module 12 as well. You know it's due a week from today, and that's it. So the remaining part of this would have been just time for you to have an office hour, but no one showed up, so I guess we'll just call it a day. So feel free to give me a call or text message. Remember, I did give you guys my personal cell phone number so that you can text me anytime you need help. So please do that. And again, I'm still asking for people. We've got a couple more weeks left, and that's about it. But if y'all want another time other than noon to help to be available for you guys, even though this will be our last lab, it doesn't mean it's our last lab meeting. You guys get a certain amount of my time for that as well. So I'll come in again next week. We'll just plan on it being noon. Uh, but I'm probably going to offer some other times too, just to make up for the 3 hours you're supposed to get every week. So, anyways, I'm going to use these times as times to get you caught up, to get you maybe uh, back in, like a lot of students have discovered that they were doing pretty well, and then the grades started to tank after this second face-to-face test. So this might be a good time for you to start asking me questions about, early on in the semester, chapter one, chapter two, chapter three, chapter four, five, six, those questions, as well as prepare for the future chapters. So I'll be filling in those times with potential office hours, but I'll be here every Tuesday at noon like I'm supposed to, unless I let you know otherwise. So have a good day, everyone, and thank you. Bye bye.